How do large language models work? The power of transformers. Section 1. What are neural networks? Just like our brains have neurons that transmit signals to one another, artificial neural networks consist of layers of nodes called neurons that process information and make predictions. To understand LLMs, we need to start with neural networks. Neural networks are computational models that are inspired by the structure of the human brain. Each connection in a neural network has a weight that determines how much influence one neuron has on another. Just like our brains have neurons that transmit signals to one another, artificial neural networks consist of layers of nodes called neurons that process information and make predictions. Section 2. From RNNs and LSTMs to transformers. In the early days of natural language processing, models like recurrent neural networks, RNNs, and long short-term memory networks, LSTMs, were used to process sequential data, like sentences or paragraphs. These models process input one word at a time, maintaining a memory of previous words in a sentence to capture context. While RNNs and LSTMs are great for handling sequences, they face a major problem. The longer the sequence, the harder it is for them to remember important details. This is due to something called vanishing gradients, where information fades as it moves through the network. Transformers were introduced to solve these issues. They use a radically different approach that allows them to process the entire sequence of words simultaneously, capturing relationships between all words in a sentence regardless of their position. This is thanks to a mechanism called self-attention. Section 3. Enter the transformer. Transformers, introduced in the landmark paper, Attention is All You Need, by Vaswani et al., in 2017, revolutionized how we process language. Unlike RNNs, which process words one at a time, transformers use self-attention to look at all the words in a sentence simultaneously. This enables them to capture complex relationships between words, even if they're far apart. Transformers work through a series of layers, each consisting of two primary components: multi-head self-attention and feed-forward neural networks. Section 4. How self-attention works. Let's dive deeper into the heart of the transformer, self-attention. The key idea behind self-attention is that, instead of processing each word independently, the model looks at how every word in a sentence relates to every other word. It does this by creating three vectors for each word: query, key, and value. These vectors are used to calculate a score that determines how much attention each word should pay to every other word. For example, in the sentence, "The cat sat on the mat," cat will pay more attention to sat because they are closely related in meaning, and less attention to on or mat. This is where multi-head attention comes in. Instead of using a single set of attention weights, transformers use multiple heads to capture different aspects of the relationships between words simultaneously. Section 5. Positional encoding. Transformers, by design, don't have any sense of word order. To solve this, they use positional encoding. This adds information about the position of each word in the sentence to the word embeddings, allowing the model to understand the sequence of words. Positional encoding ensures that the model understands where each word is located in a sentence, which is essential for capturing meaning. For example, in the sentence, "The cat sat on the mat," the word order is crucial. "Sat on the cat mat" would mean something completely different. Section 6. Feed-forward networks and normalization. After the self-attention layer, the data is passed through a feed-forward neural network, which processes each word independently. This allows the model to apply additional transformations and refine the output. Transformers also use layer normalization and residual connections to ensure stable training. These techniques help the model prevent the loss of important information and make the network easier to train. Section 7. Training transformers. Training a transformer-based model like GPT involves feeding vast amounts of text data into the model. During training, the model learns to predict the next word in a sentence, adjusting its weights to minimize the error between its prediction and the actual word. Training LLMs requires enormous computational power. For instance, GPT-3 was trained on hundreds of billions of parameters using thousands of GPUs. This intense training process enables the model to develop a deep understanding of language, allowing it to generate human-like text. Section 8. Applications of LLMs. Once trained, LLMs can be used for a wide range of tasks. They power chatbots, automatic translations, content generation, and more. For example, GPT-3 can write essays, create poetry, answer questions, and even generate code. LLMs are also increasingly being used in fields like healthcare, law, and business to analyze text data, summarize information, and assist in decision-making. Section 9. Challenges and limitations. Despite their impressive capabilities, LLMs come with challenges. One significant issue is bias. Because these models are trained on large datasets that include text from the internet, they can inherit biases present in that data. Additionally, the environmental cost of training these models is high. Large-scale training requires massive amounts of computational power, which contributes to a significant carbon footprint. And while LLMs can generate text that seems intelligent, they still lack true understanding of the world. They don't have common sense, and they may generate plausible-sounding but nonsensical answers. Transformers have redefined what's possible with natural language processing, enabling models to understand and generate language with remarkable accuracy. While challenges remain, the future of LLMs is bright, with advancements pushing the boundaries of AI applications every day. If you enjoyed this deep dive into how LLMs and transformers work, make sure to like, share, and subscribe for more content on AI and machine learning. Have any questions or thoughts? Drop them in the comments below, and we'd love to discuss. Thanks for watching. Special thanks to the research teams and authors whose work helped make this video possible.